Dear students, already we have discussed in our previous video regarding the forward difference table or forward difference operator. Today we will discuss the backward difference operator. Backward difference operator, and its notation is inverted delta. Okay, how we define it? Its definition is backward delta yi is equal to yi minus yi minus 1. Okay, just you recall the forward difference. In forward difference we are using this notation, but in backward difference we are using this notation, but concept is same, nu minus old. Okay, so now you make the table that is called difference table for backward difference table. So you consider the set of data. This is x and this is y. Okay, say this is x0, y0, x1, y1, x2, y2 and x3, y3, right? Like our forward difference, here also we use the same nu minus old, but notation is different. This is first order backward difference. This is first order backward difference. The definition is y1 minus y0, but we denote it as backward delta y1. Similarly, y2 minus y1, we denote it as backward delta y2. Here y3 minus y2, we denote it as backward delta y3. This is our first order backward difference. Then you come for the second order. This is second order backward difference. That will give us backward delta y2 minus backward delta y1. That equal to backward delta y2 square. Similarly here backward delta y3 minus backward delta y2, that is backward delta square y3. Then go for the third order. This is third order. Okay, in third order, this is the new one, this is the old one, that is backward delta square y3 minus backward delta square y2, that gives backward delta q y3. Okay, so this is the idea that how we generate the backward difference table. So like our forward difference, here we have defined backward delta yi is yi minus yi minus 1. Similarly, if we write backward delta square yi, what it gives? That is backward delta of backward delta yi. But what is backward delta yi? That is backward delta yi is yi minus yi minus 1. If you use the linearity, that is backward delta yi minus backward delta yi minus 1. So what is the definition of backward delta yi? That equal to, this is yi, so you will write this is yi minus yi minus 1 minus this is yi minus 1, so you will write it as yi minus 1 minus yi minus 2. If you expand, that gives yi minus 2 yi minus 1 plus yi minus 2. Okay, so this is the second order backward difference. Now we will summarize it. We have found out backward delta yi is yi minus yi minus 1, and also we have found out backward delta y square yi, that equal to yi minus 2y I minus 1 plus y I minus 2. Now we calculate backward delta qyi. So backward delta qyi, that is backward delta of backward delta square yi, that equal to backward delta of this delta square yi is this one. So that is yi minus 2y I minus 1 plus y I minus 2. If we apply the linearity, that gives backward delta yi minus 2 backward delta y I minus 1 plus backward delta y I minus 2. That gives backward delta yi, that gives yi minus y I minus 1 minus 2. This is backward delta yi, that will give us y I minus 1 minus y I minus 2 plus this is y I minus 2, that will give us y minus 2 minus y minus 3. Okay, so that equal to, if we expand it, that is yi, this is yi minus 1, yi minus, this is minus 1, this is minus 2, that is minus 3 y I minus 1, this is minus 2 into minus, that is plus, so 2 y I minus 2, this is I minus 2, that is plus 3 y I minus 2, then minus y I minus 3. It is almost similar to the forward difference. Okay. So finally we get, this is backward delta q yi is this. If we proceed in similar manner, can you say what is the nth difference? That is backward delta n yi. Okay, see, so we can write it as, you see, this is order 1, so we write I minus 1. This is order 2, we write I minus 1, I minus 2. Okay, this is order 3, we write yi I minus 1, I minus 2, I minus 3. Similarly, if this is order n, we will write yi minus y I minus 1 plus y I minus 2 plus, and last term is y I minus n. Okay, but what is this coefficient? As this is n, you will write this is n0, this is n1, this is n2, and so on, and this last term will be minus 1 to the power n, n. This is the formula for backward difference. Okay, now already we have discussed what is the backward difference operator and its corresponding table. Now let us come to a particular example with some data. Backward difference table. So let us consider the data x and y. Say this is 2, 4, 6, 8. This is 15, 20, 31, 28. Then the backward difference is 20 minus 15. That is 20 minus 15. That gives backward delta. That is 5. That is backward delta. First order backward difference. Okay. Similarly, 31 minus 20. That is 11, that is backward difference delta. 28 minus 31, that is minus 3, that is first order backward difference. Now you mark, actually the same thing what we have done here have also done in the first order. So what is the difference, we will discuss later on. So this is the first order backward difference. Then go for the second order. That is 11 minus 5, that is 6, minus 3 minus 11, that is minus 14. Go for third order. that is minus 14 minus 6 20. So this is the idea that how we formulate the backward difference table. Okay, now we will discuss another thing, that is shift operator. It is denoted as shift operator is denoted as capital E. How we define it? Its definition is E of yi is equal to yi plus 1. That means wherever we use the shift operator, that shifts one data to the right. Okay, yi is shifted to yi plus 1, or we can write E of fx is equal to f of x plus s. Both are same. Here we are writing in terms of y, here we are writing in terms of fx. Both are same. So now we learn three operators: forward operator, backward operator and shift operator. Okay, so now our task is we will discuss the interrelationship between these three operators. We will discuss the interrelationship between forward delta, backward delta and E. Proof of 1. Okay, so we start delta yi, that equal to, as per the forward difference operator, that is yi plus 1 minus yi. But as per the shift operator, we can write it as E of yi, and this is only yi. Okay, so if we write it as E minus 1 yi. Okay, so now we get delta yi is equal to E minus 1 yi. So that implies delta is equal to E minus 1. That is our proof. Okay, now we come to the second. So now we will prove the second property or the second relationship between the backward delta operator and E. Let us prove it. So backward delta operator with yi, that equal to yi minus yi minus 1. That is the definition of backward operator. Okay, so that equal to yi minus, you see this is shifted but backward shifted because yi minus 1. So we can write E is the shift but backward shift means to the power minus 1, because e to the power 1 means first order shift, e to the power 2 means second order shift, e to the minus 1 means first order shift but backward of E yi. Then if you take yi common, that gives 1 minus e to the power minus 1 yi. And what is the left hand side? Left hand side is backward delta yi. So backward delta yi gives this. So that implies backward delta is equal to 1 minus e to the power minus 1. So this is our proof. Okay. Now come for the third. Forward delta yi. Proof of third. Forward delta yi. What it gives? I plus 1 minus yi, you keep it as 1. Then E backward delta, you give it to yi, right? So that gives E, what is backward delta yi? That gives yi minus yi minus 1. That gives E of yi minus E of yi minus 1. E power is 1 means it will be shifted one step. So that is yi plus 1 minus yi minus 1 plus 1, that is yi. You see the right hand side yi plus 1 minus yi, here also yi plus 1 minus yi. As right hand sides are same, we can say left hand sides are same. So from 1 and 2, we conclude forward delta yi is equal to E backward delta yi. That implies forward delta is equal to E backward delta. Similarly, you can prove this part. You can show, it is a homework, forward delta is equal to backward delta E. Just in similar manner like the proof 3, you do it. Suggestion is do as proof 3. Okay, so this is the homework. You pause the video, try to work out, and you will get the answer with highest satisfaction. Now using shift operator, we will prove E is equal to e to the power hd, where d is the derivative or the differential. Okay, E is shift operator, E is shift operator, and d is derivative. Right, now you see how we are proving it. We know E of fx. What is the duty of E? Just E will shift the function to one step. E of fx is equal to f of x plus h. Right. Then expand this function f of x plus h by Taylor series expansions. That equal to f of x plus h f dash x plus h square by 2 factorial f double dash x and so on. Okay, we can write it as fx plus h d of fx plus h square by 2 factorial d square fx and so on. Okay, 1 we have taken common fx, so here it is hd plus hd square by 2 factorial and so on whole into fx. Right, but what is this? This is nothing but the exponential function e to the power hd, because the expansion of e to the power x is 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So this is nothing but the expansion form of the e to the power hd into fx. Right, so what we get? So e of fx, we get e to the power hd of fx. So that implies E is equal to e to the power hd. This is very important and interesting examples which is very often asked in the exam as a short question. Express the shift function in terms of the exponential function. Okay, so that is E is equal to e to the power hd.